Hello and welcome back. We will look at maybe two more problems dealing with entropy. So, the first one here says 5 kg of saturated water vapor at 100 degrees centigrade is condensed to a saturated liquid at 100 degrees centigrade in a constant pressure process by heat transfer to the surrounding air, which is at 25 degrees centigrade. What is the net increase in entropy of the water plus the surroundings? Okay. So, we have 5 kg of saturated water at 100 degrees centigrade. This is condensed to saturated liquid. So, saturated water becomes saturated liquid at 100 degrees centigrade. So, therefore, this is a constant temperature process. It says it is a constant pressure process, which is also what we would expect, because for example, when we were drawing TV diagrams, we saw that we have saturated water vapor here, it becomes saturated liquid here. During this process, the temperature is constant. If we were to draw the isobar will look like this. So, during this process, the temperature and the pressure both are constant. And what it says is there is heat transfer to air, which is at 25 degrees centigrade. So, which is also what we would expect. So, this is a process of condensation because vapor is becoming liquid. In this process, it has to give out heat, which is being given out to the atmosphere. The atmosphere is at 25 degrees centigrade. The temperature of the atmosphere is not expected to increase when you boil or condense water because the atmosphere is very large. We are asked to find out the net increase in entropy of the water plus the surroundings. Okay, so delta S for water and for surrounding air. So, in this process, we can, for finding out the change in entropy of the water, we can find it out directly from the steam tables. So, the condition here is 100 degrees centigrade. So, it is saturated at 100 degrees centigrade. So, we need to find out what is the pressure corresponding to that. So, let us look at the steam tables. We know it is saturated and it is 100 degrees centigrade. So, corresponding to a saturation temperature of 100 degrees centigrade, the pressure is 1.014 bar, essentially about 1 atmosphere. So, at this condition, we want the entropy of the liquid, which is this, and the entropy of the vapor, which is this. We know that the difference is essentially SFG, which is actually what we are interested in. So, that is 6.0469 kilojoule per kg Kelvin. We have 5 kg of water. So, delta capital S is m into delta small s, that is 5 into this. Which is 30.23 kilojoule per Kelvin. So, this is the change in the entropy of the water. We know that this is actually going from 1 to 2, the entropy is reducing. So, for the water this must be negative. So, delta S between 2 and 1 is what was listed in the table. So, delta S from 1 to 2 is essentially negative of this. So, we have a negative change in entropy for the water. The water is giving out heat, its entropy is reducing because it is giving out heat. So, this is something which we see. The next part of it, we are asked to find out what is the entropy change for the air. For the air undergoes an isothermal process because its atmosphere, it is very big, the temperature does not change. So, we can assume the heat transfer to be reversible because it is isothermal. So, in that case, what we can say is Q reversible is TdS for the air. If I am writing small s here, I also need to take into account mass. It is either T into capital ds or actually I should write delta S because I am writing Q and not del Q. So, I want delta capital S, which is Q reversible by T for the air. The heat transferred to the air is the heat lost by the water. So, let me find out the heat transfer for water. The water is condensing, so the heat transfer is essentially what corresponds to the latent heat. So, this is essentially m into HFG. If it was evaporating, it would be HFG. In this case, it is condensing, so it will be minus HFG. So, m minus m into HFG would be the heat transfer for the water. So, mass I know is 5 kg. HFG I need to see the tables at 100 degrees centigrade. So, if I look at the tables at 100 degrees centigrade, HFG we have used it for some other problem earlier. So, it is marked here in this red box. It is 2256.4 kilojoule per kg. So, this is essentially 11282 kilojoules with a minus sign. This is heat lost by the water. For the air, this is heat gained by the air. So, it is 11282, and the temperature of the air is 25 degrees centigrade, which is 298 in Kelvin. So, this comes out to be 37.8 kilojoule per Kelvin. This is delta S for the air. So, we have the individual values, and if we look at delta S for the universe, it is essentially a sum of this value for the water and the value for the air. Which comes out to be about 7.57. Which is the net increase. So, this is positive. So, we see that the entropy of the universe has increased by this process because we are having irreversible heat transfer from this system. We are having heat transfer over a finite temperature gradient. The liquid is at some temperature, the gas outside is at some temperature. So, there is a temperature gradient over which heat is being transferred. So, even though the temperature of the liquid itself, I mean the vapor and liquid of water itself, the temperature does not change, it is isothermal within itself, and for the air outside, the temperature does not change, it is isothermal outside, but between the two there is a temperature difference, because of which we are having a increase in entropy. So, let us look at one other problem here. It says a closed tank with a volume of 10 liters containing 3 kg of water initially at 20 degrees is heated to 180 degrees by a heat pump. Okay. So, we have a closed tank, it is possibly a rigid tank. The volume of the tank is constant, it is 10 liters, that is 10 into 10 power minus 3 meter cube, 1000 liters per meter cube. It has 3 kg of water. The initial temperature is 20 degrees centigrade. Final temperature is 180 degrees centigrade. So, this receives heat from a heat pump. So, this is our tank of water. So, it receives heat from a heat pump, thereby increasing its temperature. The heat pump is getting heat from surroundings at 20 degrees centigrade. And this is initially 20 and finally 180. So, we can run a reversible heat pump. So, it says assume that this process is reversible, find the heat transfer to the water. So, we are asked to find out this, and the work input to the heat pump, we are asked to find out this. So, this is a reversible process because we are transferring heat from using a heat pump rather than simply bringing an object in contact with this. So let us convert these into Kelvin. So this is 273 plus 20, which is 293 Kelvin. This is 180 plus 273, which is 453 Kelvin. The mass of water here is 3 kg. The volume of water is also known. The initial temperature and final temperature of water are also known. This is a constant volume process because it is a closed tank, it is a rigid tank. Of course, there is heat transfer. So, we can find out how much is the heat transfer because this undergoes a constant volume process. So, the amount of heat transferred to the water, we can try to find out if we can try to find out from the tables if we know something about the state. 3 kg of water initially at 20 degrees, we can try to find out what is the volume, specific volume of water at 20 degrees, see what would be the complete volume and then see what is the state. That would give us the initial condition. We know the mass finally, we also know the volume finally, which is 10 liters again. We can find out the final condition and then the difference between the energies of the initial and final conditions would tell us what is the heat transfer. So, from the first law we have del Q is equal to du plus del W. Del W for this is 0 because it is a constant volume chamber. So, del Q is du or Q is delta U, that is equal to m depending on what is the condition over here, m into U2 minus U1, which will tell us this. So, let us look at the condition here at 20 degrees centigrade. So, at 20 degrees centigrade, what we see is Vf is 0.001 and Vg is 57.76. Vf is 0.001002. Vg was 57.76, both of these are in meter cube per kg. So, for 3 kg, we can find out this or we can find out specific volume. V1 is equal to V2 is essentially 10 liters, which is 0.001 into 10 divided by mass, which is 3. So, we have 0.01 by 3, which is 3 in 10 power minus 3. This is the initial specific volume. Since the mass is fixed and the volume is fixed, this is also the final specific volume. So, this 0.033 lies between 0.001 and 57.76, which means this must be initially saturated. It must be a mixture of liquid and vapor. So, we can find out the initial quality. We know that V1, which is this value 0.0033, is Vf plus x into Vg minus Vf. So, we can find out x, which is essentially V1 minus Vf by Vg minus Vf. So, V1 is 0.0033, Vf is 0.001002, and we have Vg is 57.76 and Vf is again 0.001002. So, this gives us a value of 3.97 in 10 power minus 5. So, it is very close to liquid. This is x1. So, corresponding to x1, we can find out u1, which is uf plus x into ug minus uf. So, I need the values from the tables. We are at a temperature of 20 degrees centigrade. So, uf is 83.9 and ug is 2402.3. These are in kilojoules per kg. Which gives me a value of about 84 kilojoule per kg initially. So, the final state, what we know is the temperature is 180 degrees centigrade and the specific volume, this is V in case it was not clear. So, V2 is also 0.0033. So, T2 is 180 degrees centigrade. So, let us look at the tables for 180 degrees centigrade. At 180 degrees centigrade, the specific volume of liquid is 0.001127 and vapor is 0.1938. (180 degrees) is 1127 1938, and our actual V2 is 0.0033. So, it lies between these two values. So, therefore, the final state also must be saturated. So, we can find out x2. Like before, we have V2 is equal to Vf plus x into Vg minus Vf, which means that I will write this here. This is x2. This is Vf2. So, V2 is known, minus Vf2 is 0.001127, and denominator we have 0.1938 minus 0.001127. I believe that gives a value of about 4 in 10 power minus 4. Which is possibly all right because the value is closer to Vf than to Vg. This is all in meter cube per kg. So, what you are interested in is U2. So, at 180 degrees we want Uf, which is this value 761.9, and we want Ug, which is 2582.8. So, U2 is Uf plus x into Ug minus Uf. So, I am going to substitute these. Which gives me a value of 762.6 kilojoule per kg. So, we had U1 which is 84. So, 1 Q2 is mass which was 3 kg into U2 minus U1 which is 76.6 minus 84. Which gives me a value of 2035.9 kilojoules. So, what we have found out is Q, the amount of heat transferred to the water. What we need is work input to the heat pump. We need W. This is a reversible heat pump. So, it's a reversible heat pump. So, if I call this as, we are calling it as, let us say QH, that is the heat transferred from the high temperature side. So, what we know is for a reversible heat pump, QH by QL would be equal to TH by TL, which in this case is 453 and 293. Which means I can find out QL from this, that is QH into 293 by 453, which is about 1316 kilojoules. For this heat pump, if I look at numerical values, QL plus W gives me QH, or W is QH minus QL in terms of numerical positive values, taking into account already the signs and so on. So, W, or let me say mod W, is QH minus QL, that is essentially 2035 minus this, which is about 718 kilojoules. In reality, of course, for the heat pump, work is coming in. So, for the heat pump, this value of work is negative. So, it is minus 718. But if I just want the magnitude of work, it is 718. For this heat pump, Q is going out. Heat going out is negative. So, this QH is negative for the heat pump. QL is positive for the heat pump. For the water, Q is coming in, QH. So, QH is positive for the water. And for the atmosphere, QL is going out, which is negative for the atmosphere. So, we are asked to find out the heat transfer to the water, which we did, work input to the heat pump. So, the work input is this, the work itself is minus 718 kilojoules. Work input is 718 kilojoules positive, because if I say input, it already assumed that it is what is coming in. So, the magnitude of the work coming in is 718 kilojoules, whereas if I want to, if I just said work transfer for the heat pump, the work transfer would be negative with minus 718 kilojoules. So, we will stop here for today and we will continue on to cycles in the next class. Thank you.